I want to thank the organizers for the invitation and thank all of you for coming. Usually when you give the first lecture in conference, you can start by saying that so far all lectures have been perfect. And looking at the program of this conference, I'm pretty sure that with the possible exception of the following lecture, the last speaker in the conference will still be able to say that all lectures have been perfect. So I want to thank the organizers for that as well. The title is Graphs, Vectors, and Integers. And the focus will be the interplay between techniques and ideas from graph theory and combinatorics and other areas of mathematics, including geometry and number theory. Okay, so the main combinatorial object of study will be this Cayley Sum Graphs, which are basically almost the same as Cayley graphs, but maybe they are more symmetric. And I'll tell you what they are, and I want to tell you to show you some applications. So we'll have a billion group. All my groups and all my graphs here will be finite, and H will be this abelian group, and S will be some subset of the group. And then with S we can define a Cayley graph, G of H and S. And this is a graph whose vertex set is just all the elements of the finite group H, and 2 are adjacent, and B are adjacent if and only if their sum belongs to this set S. Okay, so we see here, for example, the group is a cyclic group with 8 elements, and the set S is 1 and 3, and you see that 0 is joined to 3 and to 1 because the sum is 3 and 1. 1 is joined to 0 and 2 because these are exactly the two numbers whose sum belong to S, and so on. So in this case, we just get a cycle. Okay? And there are two simple facts about those Cayley sum graphs. So one of them, which is really obvious from the definition, is that this graph is regular, and the degree of regularity, the number of edges incident with any vertex, is just the cardinality of the set S. I should say that for that we may have up to one loop in some vertices. If 2x is in S, then x is connected to itself. And if we have a loop, we count it as 1 for the degree, for these to hold. And then, of course, for every element of S, we get one neighbor of any other vertex. So that's one obvious fact. The second one will have to do with the eigenvalues. So much of the lecture will be will deal with the spectral properties of graphs or with their eigenvalues. And for this, we have to know what is the adjacency matrix of a graph. So when we have a graph G, the adjacency matrix is a matrix whose rows and columns are indexed by the vertices of the graph. And in place A, U, V, we have 1 if U and V are adjacent. We have 0 if they are not adjacent. So this is a symmetric matrix. Because of this, it has real eigenvalues and an orthonormal basis of eigenvectors. And these eigenvalues, we call them the eigenvalues of G. Now, another fact that is pretty simple, and to stress it, I use the microphone, as you see, is that the eigenvalues of G, in this case, you can express them by character sums. Namely, for every character of the group, you can take the sum over all the elements of this set S, of the character chi in S. You take this sum, you take the absolute value, and it will be either plus or minus. So this is because it's easy to see that if you look at the characters themselves, they are eigenvectors of the square of the adjacency matrix with eigenvalues which are the absolute value squared. And one can determine also the the sign here, but usually we will not care about it. Now, basically, these two facts together, and especially the one about the eigenvalues being expressed as character sums, enable us to use the relation, the known relation between the spectral properties of graphs and their structural properties and known results or results that we can prove about character sum estimates to deduce to get some insight about some problems about the graphs. And this is useful in the study of problems naturally in extremal graph theory and combinatorics, but also in other areas like additive number theory, geometry, and information theory. And I'll try to give some examples. Okay. So this is a kind of a summary of what would is focus, and now we'll have a few examples, and the main two will be a geometric one and one from number theory. But we will see some combinatorial and graph theoretic problems on the way as well. So here is a geometric problem. It's a problem in extremal combinatorics, and I'll tell you something about its motivation also soon. So let me denote by f of n the maximum possible norm of a sum of n unit vectors in Euclidean space. So we have n unit vectors in Euclidean space. We don't specify the dimension, so it can be, the dimension can be n, like the span of these vectors. And we want to maximize the norm of their sum, so we sort of want that they all will point in the same direction in some sense. And on the other hand, we want that among any three of them, some pair will be orthogonal. Okay, so this is, and that's why I called it nearly orthogonal in some sense. So not every pair is orthogonal, but among any three, two are orthogonal. And the problem suggested by Lovas was to try to, or is to try to determine or estimate this maximum. Okay. Now, why would we want to do this thing? So the motivation comes from trying to estimate the maximum possible Shannon capacity of a graph, and I'll tell you something about this. It's a fascinating subject by itself. Maximized over all graphs with n vertices and independence number 2. So this is a question that comes from information theory, and indeed you see here an example of or a picture of a channel, and you see here a Claude Shannon, the founder of information theory, and he's trying to send in the channel some message to a Lovas that you see on the right side. And being a little bit more formal, let me tell you something about what Shannon defined in 56 as the zero error capacity of a noisy channel. That's the title of his paper. I should say that this is what is called a zero capacity information theory, or zero error information theory, which is some part of information theory that is more combinatorial. So here is a story. We have in a channel, we have some symbols, some finite set of symbols. You should think about them as the alphabet. These are the things that you can send, or that Shannon there in the picture could try to send to Lovas. But some of the pairs of symbols are confusable. Confusable maybe because they look to each other, or because the channel is such that one of them can be perturbed and becomes the other. So for some reason, some pairs are confusable. And then we can define a graph of the channel. And the graph of the channel has the vertex set, the set of all symbols. So this would be the finite alphabet, which we denote by x. And two elements, x and y of x, will be adjacent if x and y are confusable. Okay, so that's just a representation of the channel. And now, if you think about it, then the maximum number of one-letter messages that can be transmitted with no danger of confusion, with no error at all, is exactly what is called the independence number of the graph G, namely the maximum number of vertices, so that no two of them are adjacent. Right? So here we have a picture. maybe the graph of the channel is a cycle of length 5, and maybe the letters are what you see there. So I'm not sure how good an example it is, but you see that H and N are confusable because they look similar to each other, and N and P are confusable because they look similar to each other. I must say that from my angle, everything looks confusable to each other, but hopefully it's a... But on the other hand, the N and B are not confusable, so they don't look like each other. So if they want to send a message of one letter, they can agree that they are going to send only either N or B. There is no danger of confusion, and obviously with one letter, that's the maximum, that's the best that they can do. Okay. But a common theme in information theory is that things become more efficient as the length of the communication grows. And this is what we try to capture by the Shannon capacity of the graph or of the channel. We try to send long messages. So the Shannon capacity of the graph or of the corresponding channel will be the supremum number S, so that for large K, the maximum, if we are using long messages, the maximum number of K letter messages that can be transmitted with no error is at least S to the K. Right? And the good way to think about it is that this is the effective size of the alphabet. If we have a channel and the Shannon capacity is 10, it's exactly like having an alphabet of size 10 in which there is no confusion at all. So you can just use all the 10 to the K distinct words of length K. Okay. Now, if you think what this means as a function of the graph, then this Shannon capacity is the limit as K tends to infinity. K is the length of the message, of the independence number of G to the K, of the kth power of G. How is this kth power defined? So the vertices are vectors of length K of vertices of the original graph, and two such sequences of length K are adjacent if in every coordinate they are either equal or adjacent. You see, because the way that two sequences of length K will be confusable, I need that in every coordinate it will be confusable or maybe equal. Then I'll not be able to, or they can confuse with each other. But if there is even one coordinate in which they are distinct and non-confusable, then there is no danger that I mistake one of these sequences to the other one. Okay? So it means that the definition, we have this definition of the kth power of the graph. Sometimes it is called the n power, so this is one of the powers of the graph. We have to take the independence number raised to the power k, and we have to take the kth root of it. And because of some super multiplicativity and Feket's lemma, it's easy to see that this limit always exists. So this limit, which is also equal to the supremum over all k, always exists, and this is called the Shannon capacity. Now, the Shannon capacity of a graph G is very hard to understand, and I wrote here, and this is quite striking if you haven't seen it before, that it is not known what is the value of this for a cycle of length 7. Now, you cannot think about many graph invariants or natural or interesting graph invariants that we don't know to compute for a cycle of length 7. So it really shows that, well, because it's defined in terms of a limiting process, then it's not, there are some bounds, but we don't know what the value is. On the other hand, there are several upper and lower bounds, and the best known upper bound, which is often also the best bound that we can prove, is a geometric quantity that I'll not define. It's called the Lovász theta function of a graph, and this was defined by Lovász in 79. And for some graphs, not for many, but for some graphs, it actually gives the correct value of the Shannon capacity of a graph. For example, for any graph that is isomorphic to its complement and is vertex transitive, it gives the truth, and the cycle of length 5 is an example, and the Shannon capacity of it is indeed square root 5. So the number of messages, of long messages, here long for the specific value of a cycle of length 5, it's enough that it will be of length at least 2. But the maximum number of long messages that we can send with no danger of confusion with the channel that I showed you before, this 5 cycle, if the length is k, it's 5 to the k over 2. Okay. Now suppose we want to know, and this is a natural question, we want to know how better the Shannon capacity can be from the independence number. The independence number is what we can do with messages of 1 letter, and the Shannon capacity is what we can do with long messages. So a big gap would say that we are making a lot of progress. The natural question is, what is the maximum possible Shannon capacity of a graph with independence number 2? So the independence number 2 is essentially the smallest interesting case, because independence number 1 is a complete graph, and for a complete graph, the Shannon capacity is equal to the independence number. It stays 1. Nothing interesting is happening. So this is not known, and maybe I'll also flash it here. It's even not known if it is finite or infinite. So that looks like a fundamental problem, that we don't want to compute some specific number. We just want to understand if it's finite or infinite. And it's exactly equal to the following, to the kth root of what is called the multicolor Ramsey number R3K. So that's also a question that has been considered quite extensively, one of the problems of Erdős. And it asks, what is the maximum number of vertices in a complete graph so that it is possible to color the edges of the complete graph by k colors so that no color class contains a triangle. Okay? And exactly if we think about this number for large k and we take the kth root and we go to a limit, then this is equal to the Shannon, to the question about the Shannon capacity, the maximum possible Shannon capacity of a graph with independence number 2. The number of vertices can be as large as we want. And as I wrote here, it is known that this number is at least 321 to the 1/5. So this is just because there are some specific examples. They come from a related problem of Schur, who was interested in coloring the integers from 1 up to n with no monochromatic solution to the equation x plus y equals z. And somehow this is related to the Ramsey number, and some examples for this give us the best lower bounds that we have. But as I said, the really kind of fundamental question is to decide if this number is finite or not. Okay, so we don't know to solve this question, but we want to at least try to say something meaningful about the maximum possible theta function of a graph on n vertices with independence number 2. Right? So this is natural. I mean, the theta function is usually the best known upper bound that we know. So instead of studying the Shannon capacity, we can look at the theta function. And it turns out that this question is equivalent. So again, I didn't define the theta function, so it's not, so I cannot show why it's equivalent. But it's equivalent to this question of deciding what is a maximum possible norm of a sum of n vectors so that among any 3, some pair is orthogonal. It's an equivalent question. It's not, you still have to play with f of n a little bit to get the value of this question about the theta function, but there is a formula relating the two things. So that's the motivation, and well, that was the motivation, but maybe it's a natural question in itself. And let's see what is trivial. So what is trivial is that this f of n is at least square root n, because we can just take n vectors that are mutually orthogonal. So of course, among any 3, you have a pair that is orthogonal. You have even more. And then the norm of the sum is square root n. You can improve the constant a little bit by taking 2 disjoint systems of n over 2 pairwise orthogonal vectors and making sure that they will point in the same direction. But this would still behave like square root n. On the other hand, there is a nice short proof of Konyagin that shows that this, okay, so I said trivially the maximum is at most n, right, just by the triangle inequality. And there is a clever but short proof of Konyagin showing that the maximum cannot be more than some constant n to the 2/3. Okay? And with Kashin, he had an example that the maximum can be almost that. So it can be n to the 2/3 over log n. And I could improve that, so I could get rid of this log n. So really, the maximum is constant n to the 2/3. We don't know the precise constant. And if you translate it to the lower theta function, this will tell us that the maximum value of a theta function of a graph on n vertices with independence number 2 is some constant n to the 1/3. So this is so it means that this is not a good way to decide if the maximum possible Shannon capacity is finite or not, because this is growing with n. But still, after a while, these questions become interesting in their own. And what I want to show you is something about the lower bound construction. So we want these vectors, so that among any three two orthogonals, they are unit vectors, and they all sort of point in the same direction. And because this is kind of an interesting application of a Cayley Sum Graph with some nice properties. Now, I wrote here the specific graph. It's not so important, but let me just say it. So the group is an elementary abelian 2 group, so just a binary vector of length 3k, and addition is addition modulo 2, coordinate-wise. And then I have to tell you when two things are adjacent. So they are adjacent if and only if their sum belongs to some set S. Here, sum and difference is actually the same. So here, Cayley Sum Graph is also a Cayley graph because the characteristic is 2. And the example is that you take all the sums of a little u0 plus little u1, where little ui is in capital UI, where the sets u0 and u1 are defined as written there. So you can think about the finite field with 2 to the k elements. You can represent it by binary vectors of length k, just coefficients of polynomials. If you represent the field as polynomials modulo some irreducible polynomial. And then each field element is a vector of length k. And we take the concatenation of x, x cubed, and x to the 5. And we also, let's say, look at the least significant bit of x to the 7. And if it is 0, then it gives us one set. If it is 1, it gives us another set. And we take all the sums of those elements. And again, as I said, it's not so important, just to give you a feeling of this graph. And so you see this graph has the number of vertices, which we denote by n, is the number of elements of the group. So it's just the number of binary vectors of length 3k. So it's 2 to the 3k. It is regular of degree, which is the cardinality of this set S. And the cardinality of S is a product of u0 with u1. And one of them is of size 2 to the k minus 1, and the other is of size 2 to the k minus 1 because we threw the 0 vector. So the degree of regularity is roughly a quarter n to the 2/3, if we want it in terms of the number of vertices. And then it can be shown, and here you already use something, so by some known properties of BCH codes, it follows that this graph is triangle-free. So this is a rather elementary effect. The other one is eigenvalue bound, and this is a deeper effect, so that's a so-called Carli-Tsuchiyama bound, which is basically a special case of Weil, a famous theorem. And it tells us that every eigenvalue besides the biggest, for regular graphs, the biggest eigenvalue is always the degree of regularity. But every other eigenvalue here in absolute value is at most some constant times n to the 2/3, or 2 to the k. And we are specifically interested in the smallest eigenvalue, namely the most negative eigenvalue. The trace here is 0, so the sum of eigenvalues is 0, so the smallest is negative. And the question how negative it is, it's not very negative. So in absolute value, it's not more than 9 times 2 to the k or so, and 2 to the k is about n to the 1/3. So this graph has some nice bounds on the eigenvalues. And And then just look at the adjacency matrix of this graph. So remember that this is 0, 1 matrix, and we have 0 when things are not adjacent and 1 when they are adjacent. This is A. Now if we take lambda was the absolute value of the most negative eigenvalue, and we increase all the entries in the diagonal by lambda, so we look at lambda I plus A, then this will already be a positive semi-definite matrix, because we increased every eigenvalue by lambda, and lambda was absolute value of the most negative one. And then we divide it by lambda, so now on the diagonal we have 1s. So this is a positive semi-definite matrix. It has 1s on the diagonal. Because it's a positive semi-definite matrix, we can write it as a gram matrix of some vectors. So we can write it as a C transpose for some matrix C, and then the rows of C will be vectors, and they will be actually unit vectors because in the diagonal here we have 1. So these are unit vectors, and because the graph is triangle-free, whenever we take 3 of our vectors, then in the 3 corresponding places in the matrix, we see 0 in some place, because the graph is triangle-free. So that exactly means that one inner product is 0. So among any 3, some 2 are orthogonal. And on the other hand, if we want to compute the sum of VI norm square, if you think about it, this is just the sum of all the entries of this matrix. And the sum, because in the entries we have the inner products of Vi times Vj. In the diagonal we have n, so this is n, but the more important thing is that we have n times d places, because the graph was d regular. In every row we had d non-zero entries. And then in each of these places we divided by lambda, so you don't have 1, you have 1 over lambda. So this gives us nd over lambda. D was roughly n to the 2/3. I don't care about constants now. Lambda was roughly n to the 1/3. So this product gives us n to the 4/3, and when we take square root, then we get the bound we want. You wonder, yeah. So somehow watching the people in the front rows that have to look like this, I hope you survive this lecture, but maybe, okay. So this, with this I finish this geometric example, and I want to talk about the second part. And let me say, I should have said it in the beginning, so if there are any questions in between or comments, feel free to shout or scream or to stop me. So if, yeah, because you know, always at the end of the lecture there is this embarrassing moment when the chairman is asking if there are any questions and nobody is asking anything. So feel free to ask something already or think about some things that you will want to ask at the end. Okay, but we'll. Okay, so here is something else, but still I would use the spectral properties of Cayley Sum Graphs, and this is in a joint work with Jean Bourgain. And the motivation is sum product theorems. So, you know, usually we learn to add and multiply integers, maybe in the first grade of elementary school. And it's quite striking to observe that even now, which is quite some time after that, at least for some of us, we still don't really understand the intricate relation between sums and products of integers, even of integers, right? And one thing that illustrates this is the following conjecture of Erdős and Szemerédi that is still wide open, so that's from '83. And they say that if you take a set A of n integers, then either you have many sums of pairs or you have many products of pairs. So we have a set A, what I denote here by A plus A, I mean the sum of all little a plus little a prime with A and A prime belonging to A, and same for the product. And what is written here is that the conjecture is that always at least one of them is close to n squared. It will never be more than n squared, or n choose 2 in fact, but plus n, never mind, something like n squared over 2. But the conjecture is that it should be almost z. Now you see, a set can be an arithmetic progression, and then the number of sums is only 2n minus 1. It can be a geometric progression, and then the number of products is only 2n minus 1. But the conjecture says that it cannot be close, in some sense, to an arithmetic progression and close to a geometric progression together. Right? So this is still wide open. Erdős and Semredy themselves proved some non-trivial lower bound, and this has been improved many times, and the best known lower bound is due to Konyagin-Shkredov. This is from the last few months. And it gives a lower bound of n to the 4/3 plus delta for some specific small but positive delta. So this is some product. Now, motivated by this, Bourgain, Katz, and Tau formulated and proved the same thing for finite fields. And there it turns out that you can prove the following. You have to look at prime fields because just any finite fields would have subfields, and subfields, of course, are closed under sums and products. But in a prime field, you don't have a subfield. And the following is true, that for every positive epsilon, there is some positive delta, so that for any prime p and any subset A of the finite field with p elements, which is at most p to the 1 minus epsilon, right? So we have to limit it because, of course, the number of sums and the number of products will never be more than the whole field. Then the sums or the products grow significantly. So there are at least a to the 1 plus delta, either the number of sums or the number of products. And the proof here is very different from the proof for the real or complex case, but the motivation comes from the same kind of thing. And this has lots of application in incidence geometry, in number theory, in group theory, also in theoretical computer science, in the construction of what's called extractors. So it has, okay. Now we want to consider some very extreme case. So what if we are in the extreme case that A times A is equal in cardinality to A itself? Well, you can shift it. It's essentially equivalent to saying that A itself is a multiplicative subgroup. It can be a coset, but we may assume that it's a multiplicative subgroup. So let's look at the multiplicative subgroup of the prime field Fp. Okay? And I'll denote, since I'll have many multiplicative subgroups, I'll denote by this bold triangle. This means that A is a multiplicative subgroup of Fp. Right? The multiplicative group of finite field is cyclic. So for every number d that divides its order, there is a unique subgroup of order d. And we want to know something about them. And we want to know about the additive structure in them, because indeed we want to understand this relation between a product and in sum. And maybe the most basic question, although I'll later talk also about some more complicated ones, but the most basic question is when can we ensure that this multiplicative subgroup is not sum-free, has one additive relation, has x, y, and z, so that x plus y equals z. Because it's a subgroup, we can divide by z, and this is equivalent to saying that it has a solution to x plus y equals 1. Now, it makes sense to suspect that when the group is very big, the multiplicative subgroup, like everything, then it would have relations. When it's very small, like -1 and 1 only, then it will not have such a solution, maybe. And we want to know something of this form. And there is the following fact. This follows from many known things. And so if it's big, indeed, if the multiplicative group is of size at least p to the 3/4, then there must be xy in A, so that x plus y is 1, or as I said, it's the same to talk about x plus y is 1 or x plus y equals z. Namely, it cannot be sum-free. And this p to the 3/4 is probably not tight. And one thing we proved is that there are infinitely many primes p, so that in Fp you have a multiplicative subgroup, which is pretty big, well, not p to the 3/4, but p to the 1/3, and no xy in A satisfy x plus y equals 1, so it is sum-free. And although this proof is less combinatorial, I want to tell you briefly to sketch it, because I think it's very nice. So it combines some simple tools from Galois theory and some results about what is called the Linic problems, a quantitative version of Dirichlet theorem about primes in arithmetic progression. So let me just say quickly something about this proof. And okay, so here is a more detailed statement of the theorem. It says the following: if d is an integer, and we have to assume that 6 does not divide d, d will be the size of this multiplicative group that I'm going to look at, then there exists some set ED of not too many primes, d square over log d primes. These are the bed primes, maybe. And then for any other prime which is not in ED and is 1 modulo d, so you have to be 1 modulo d just to have a subgroup, a multiplicative subgroup of size d. We want p minus 1 to be divisible by d. So if a prime is not in ED, then this multiplicative subgroup of size d is indeed sum-free, does not have a solution. And then the question is how small is the smallest p that is not in ED, because this gives us a large multiplicative sum-free subgroup, because its size is d. And then this is written here. So the smallest p not in ED, it satisfies for most d, sort of if we take a random d, then p is at most constant d cube. For every d, p is at most constant d to the 5. And for smooth d, whatever that means, no big prime divisors, then this p is at most d cube. And let me tell you how this goes. So it's short, although I mean some parts I'll not show, but the basic idea is short. So take a primitive dth root of unity, complex. This is xi here, e to the 2 pi I over d. And then you look at the cyclotomic field, which is just a field obtained from the rationals by joining to them the root xi. And then you can check that because 6 does not divide d, then xi to the I plus xi to the j is never 1. So it's just some statement about complex numbers. It's very easy to check. I should say that one can look at more complicated equations, and then what is written here is basically a special case of a famous theorem of Mahler's that tells us something about solutions in units for equations like this. But here the equation is simple enough that we can do everything explicitly. And, okay. So we know that there is none of this is 0. And then we can define the following product A. So it's just a product over all pairs I and j of c to the I plus k to the j minus 1. So it's some non-zero thing. And this thing is invariant under Galois conjugation. So if you map xi to the r for some r that is relatively prime to d, then this product stays the same. And because of this, it's an integer. So this is really an integer. And the size of this integer is, of course, less than 3 to the d squared, because it's a product of less than d squared things, and each of them is of absolute value less than 3, right? So this number is not divisible by too many primes. And our set ED will be the set of all primes p which are 1 modulo d, and that divides this A. Okay? And just by some trivial estimates, then the cardinality of this ED is at most d squared over log d. Basically, each of these primes is at least d. Right? So you can even improve the constant here. I don't care about this, but so ED is not too big. And now suppose we have a prime p which is 1 modulo d and is not in ED. So somehow, so the nice thing is that whenever you take I and j and you look at the norm of xi to the I plus xi to the j minus 1, so it's just this element multiplied by all its conjugates, all the things obtained from it by mapping xi to the r, for r relatively prime to d. So this will also be an integer, and it will divide A, because all those things appeared in A. We took all the product of all these things. So all these norms are non-zero modulo p. Okay. And now what you can do, you take an element g, which is of order p in the multiplicative group of fp. Since p is 1 modulo d, then there is, as I said, the multiplicative group is cyclic. It has a unique group of each order that is divisible by D, so we take it. And we have this element of this order. And then we define a ring homomorphism, so we just map this G, or we map, let's say we go from Xi, so we map Xi to G. Okay? And so I'm trying to do everything here in a very elementary way, and that's why I don't even mention the word prime ideal, although I guess I just did, but you can ignore it. So it is it's really very simple. So you think about this ring of integers with Xi, so just polynomials with Xi, but you think about the elements modulo P, and you map Xi to G, and you extend it to a ring homomorphism, and it works well because Xi is a primitive root, complex primitive root of order D, and so is G. So everything will be mapped nicely as we want. And the important thing is that the map or the image of Xi to the I plus Xi to the J minus 1 for each of those I and J is never 0, because we know that the norm of this element is not 0. It's not divisible by P. It's some integer that is not 0 modulo P, which means that we can multiply this thing, Xi to the I plus Xi to the J minus 1, by all kinds of other polynomials and get something that is mapped to some non-zero element, so it means that this is not 0. And this is just what we want, right? Because it means that the image of this pi of Xi to the I, namely G, G squared, G to the 4, and so on, the multiplicative subgroup of Fp, is indeed sum free. It doesn't have any solution to G to the I plus G to the J equals 1. Okay? So the only thing that remains to do is to estimate the smallest number P not in ED. Okay? And this is where you use some facts from analytic number theory, and as I said, specifically from the study of the Linux problem about the smallest prime in a given arithmetic progression. And basically, so here I'll not say much, but just it's the estimate for every D that I mentioned, that this P is at most D cube, follows from two papers by Xyloris, but really this is just optimizing a method of Heath-Brown. Then the estimate for most D, whatever most means, follows from the Bombieri-Vinogradov theorem. And the estimate for smooth D is more complicated, but it follows by adapting the known techniques in the literature about the Linux problem. And I wrote here that you basically use results of Ivanitz, Heath-Brown, Huxley, Jutila, Gallagher. You just kind of follow the same things, and it gives those estimates. So maybe this was too fast, but somehow it gives you the flavor of things. So that part was more maybe number theoretic, using algebraic and analytic number theory. And now I try to go back to my Cayley Sum Graphs, so to combinatorics. So what about more complicated additive relations? At the moment, we just talked about the most basic relation, x plus y equals 1 or x plus y equals z, but you can ask about more complicated ones. And here is a specific question by Sun, recent question. So he conjectures that the following is true. For every prime p bigger than 13, it was very specific. What is written here is not true for 13, but for every prime p that is bigger than 13, then you can take all the p minus 1 quadratic residues modulo p, p minus 1 over 2 quadratic residues modulo p, put them along a cycle, and the sum of every two adjacent ones will also be a quadratic residue. Okay, so this is, and here is an example. P is 17. The quadratic residues are 8 quadratic residues. They are 1, 8, 13, 2, 16, 9, 4, and 15. And you can check, and here I ordered them. You should think about this as ordered along a cycle. And indeed, the sum of every two consecutive, let's say 8 and 13, is 21, which modulo 17 is 4. So it's again one of the quadratic residues. And the same for every pair of consecutive ones, including the 15 and 1, because this is along a cycle. Okay, and you want to know that this is true for every p. bigger than 13, and indeed that's the case. And in fact, we could prove with Bourgain something more general, at least asymptotically, although we did bother also to prove this statement for every p starting indeed from 17. So it is. So the following is true. I mean, of course, the quadratic residues is a multiplicative subgroup of CP. But we can look at smaller multiplicative subgroups. And still something similar is true. Namely, whenever you have a multiplicative subgroup and its size is just a little bit bigger than p to the 3/4, so there are some logarithmic terms, but here I wrote p to the 3/4 plus a little bit, then always it is possible to put the elements of A along a cyclic permutation so that the sum of every consecutive pair is also an element of this multiplicative subgroup. And if we insist on talking about the quadratic residues, let me say also something that is more general than this. So suppose R is fixed, and we take a prime p that is sufficiently big as a function of R, then you can take the quadratic residues, put them along a cycle, and it's not only the case that the sum of every consecutive pair will be a quadratic residue, but also the sum of every pair of distance 2 and distance 3 and distance 4, and so on up to distance R, so if p is big enough. And I want to tell you something about a sketch of how, of the proof, let's say, of the first theorem, where you will see how the Cayley Sum Graphs appear. So somehow it's natural to look at the following Cayley Sum Graph here. The vertices will be the elements of Fp, but you think about it as an additive group. So you forget the multiplication. You think just about the addition. And then 2 are adjacent if and only if their sum belongs to A, to the multiplicative group, because I'm trying to find a lot of pairs whose sum belongs to A. Okay. So this is this Cayley Sum Graph. Now I wrote here, but this is just a notation, that an ND lambda graph is a d-regular graph with n vertices, so that the absolute value of every eigenvalue besides the trivial one is always d, corresponding to the all one eigenvector, but all the others have absolute value at most lambda. And somehow people looked at this because it can be shown that such graphs in which lambda is much smaller than d, they behave like random graphs. So they have some strong quasi-random properties. Okay, so this is an ND lambda graph. And then the claim is that by Vel, or actually here you can get a simpler proof by using some properties of Gauss sums. So this graph, the Cayley Sum Graph, where the group is the additive Fp and A is a set of generators, or the set that tells us which pair are connected to each other. So this is a pk p to the 1/2 graph, meaning it has p vertices, of course. I mean, Fp has p vertices. It's regular of degree k, that's just the cardinality of A. So the only thing that is needs some explanation here is that lambda is at most p to the 1/2, and this basically follows from Vel, for example. Okay, so if p to the 1/2 is significantly smaller than k, then this graph looks like a random graph. Okay, and then by something we proved long ago with Fen Chang, sometimes it's proved some version of this is called sometimes the expander mixing lemma. We know that for such graph, the induced subgraph on any not too small set of vertices has the right number of edges, because the graph is quasi-random. And here specifically, we look at the induced subgraph on the multiplicative group A itself. Okay, and this is regular of degree, and if you think about it, so it is regular because it's a multiplicative group. Let me not, this is a simple thing. And it is regular of the right degree. And the right degree is k² over p, because sort of the probabilities that something is an edge is like k over p, and you have, let me just say that the right degree is k² over p. So this is the induced subgraph. Now by eigenvalue interlacing, so this an induced subgraphs, we know that the eigenvalues of it interlace the eigenvalues of the big graph. And because of this specific graph has now k vertices, is regular of degree d, and still the maximum absolute value of any non-trivial additive value is p to the 1/2, which with our choice of the parameters is significantly smaller than d. And then we can use a result of Krivulevich and Sudakov about ND lambda graphs. There's such graphs in which lambda is significantly smaller than d are Hamiltonian. They have a Hamilton cycle. And if you think what a Hamilton cycle is, then a Hamilton cycle in this induced subgraph is exactly a cyclic permutation of the elements of A, so that every two consecutive ones, the sum of them belongs to A, because this was the way the Cayley Sum Graph was defined. Now this was theorem 1, and theorem 2 basically follows in a similar way by using another result about ND lambda graphs. That's a more recent result by Allen, Bocher, Han, Koyakawa, and Person. And it says something about the existence of powers of Hamilton cycles in ND lambda graphs, and you basically plug it in the same way. Let me just finish by mentioning two open problems that are sort of obvious, maybe. So the first is about sums of nearly orthogonal vectors. The first example that I talked about, it's natural to try to extend the 3 to k, and you can ask, and this will again correspond to the maximum value of the theta function of a graph with independence number k. So what is the maximum possible norm of a sum of n unit vectors so that among any k of them, some pair is orthogonal? And it can be shown that, and this we showed some time ago, that this is most n to the 1 minus 1 over k. You see if you plug k equal to 3, that's n to the 2/3 we had before. And something new, so this is more using some probabilistic arguments and some tensor trick, but let me just, so one can show that for every epsilon there is some k, so that for this case the value is at least n to the 1 minus epsilon. So I find it geometrically it's quite surprising that you have all these vectors and they really, well, in some sense, they really point in the same direction, and still among any 1,000 of them, maybe some pair is orthogonal. So it's not, but the dependence of k epsilon and epsilon is very bad, so there is a big gap. One should understand better what's going on. And about this number theory question, so there is this gap between the upper and lower bounds, the p to the 1/3 and p to the 3/4, for just getting in multiplicative subgroup of a prime field one additive relation. And it looks, so there are reasons to think that both bounds are not tight. And in fact, if we assume some square root cancellation in Fourier coefficients of multiplicative groups, so some standard conjectures in number theory, then the p to the 3/4, one would be able to improve it to p to the 2/3. But actually, there is another heuristic. So some of the heuristics that says that multiplicative groups are random for the purpose of addition suggests that the answer here should be square root p. But I think it should be difficult to, maybe very difficult to improve the lower bound or to improve the upper bound. So maybe this will have to wait for someone for the next anniversary of the LMS. And with this, I'll finish and thank you for your patience.
Yes, if this is simple or you cover this, and please excuse me for asking, but there was a mention about how the Shannon capacity was hard to compute. Why is that?
Is it how is Shannon capacity?
Well, why is it hard to compute?
Why it is hard to, well, according to the definition, you kind of have to look at infinitely many powers of the graph and compute the independence number there. So it's not clear what to do, but I guess that's more in kind of an experimental fact. We don't, it's not even known that the problem, given a graph and given a number alpha, decide if the Shannon capacity is smaller or bigger than alpha is decidable. So by hard, I mean really hard, not much harder than NP hard or something. We don't know it for a cycle of length 7, right? But I guess because it is defined as a limit, and there are examples kind of that show you could hope that this function alpha of g to the k to the 1 over k behaves nicely, and you will, and somehow one can give examples, but examples of big graphs, for which this function for a while, maybe for k equals 1, 2, 3, 4, up to a million, this stays a very small number, 10. And then for 1,000,001, it jumps to 1,000,000, and it stays near 1,000,000 until you go to power 1,000,000,000, and then it jumps again. But of course, for such examples, the graph has to be very, very big as a function of all these millions and millions. So I just say that it's a quantity that we don't really understand. And so, yeah. And thanks for asking a question.
Other questions?
Okay. Well, it's enough.
If not, let's
Thanks.
thank